Okay, so we are on YouTube now. Welcome people from YouTube for another Friday, another quantum hardware section. And today I'm planning like to finish the things I start but uh, could not conclude in the next week, the next Friday, and perhaps in the end we make an exercise to to try. And in this part of the course we are done today. That's the about quantum optics, quantum computing based on quantum optics. And then the next Friday we start like using more quantum electrodynamics effects. So okay, let me share. Okay, so I will start with the whiteboard. Continuation from the last part. Just to remember, we were like defining we are in this box 7.4. That's the quantum Threading gate. And we have a jaw like that. This one doesn't do it now. We have a C wire with a Kerr medium, nonlinear medium. And coupled to this medium is some beam splitters. A, B. This means here. This figure is in the book. You guys can look there. Something like this. You see, B, C prime, B prime, A prime. Okay, so we finish in the last um, lecture. We like conclude that we could write this. I'll call this like the U mode. This is U. That is B, K, B delta. Where K is the operator related to the nonlinear media. In B are the operators related to the beam splitters, the two beam splitters. And we conclude that we could find, I didn't show like explicitly this because the calculation is very long, so it's probably we'll have to see all the details. You would need like a full lecture, 1 hour lecture. So, but I give you guys in the last lecture just like the main steps necessary to found this for you. Okay, this is the equation 747, and we also conclude that this would be equivalent to write in this way: I over 2 b daga b exponential psi over 2 c daga c a daga b minus b a daga exponential minus I pi over 2 b daga b exponential I c over 2 a daga a c daga c exponential X over 2, B daga B, C daga C. So I think we stop here in the last lecture. The details how to find this, you guys can like check in the previous slides from the last lecture. So we can see here these terms like the first and the third, like this term here and this term here. So these two terms, they are just B dash B. They are just like phase shifters. Phase shifters in B mode. Just to remember, like remember the P for represents the phase shifter, the P operator applied for, let's say, state one with the state with one photon. This gives like a phase one. And when you have no photon, the vacuum, of course, we have the vacuum, right? If the phase shifter will not like modify the vacuum state. So these terms here will contribute only with phases, like we could see, like if we have I over 2, B daga B, B, B daga B applied, let's say, to 1, we could like B daga B, make an expansion like 1. And this would have like 1 plus minus I pi over 2, and B daga B applied to 1, we already know is just 1. This is annihilate this photon, so we have the vacuum, but then we have this creation that creates a photon. So this state is simple 1 plus minus I pi over 2 plus high order terms 1. And this is just the exponential of plus minus I pi over 2 1. That in the end is exponential I plus minus pi over 2 contribute only with like a phase. Okay, and this applied to the vacuum is 0, right? The state is pi over 2, B daga B applied to the vacuum. When you make this expansion, when B applied to 0 is 0, so do nothing. So in the expansion will be 1 plus minus pi over 2, B daga B, high order terms, applied to 0. So this applied to 0 is 0, and we have only this term. So do nothing, the vacuum. Since it's a phase shifter, right? If you are in the vacuum state, nothing will happen. And the last two terms are phase shifters. Phase shifters that come from the cross-phase modulation. Let's return here to see the figure. So this is like phase shifters, these two terms here. But that's true. This and this. That is actually relate this term C. It's appear here. C with the modes B and A. And again, we could question.
Oh shit! Go back to that blue equation. You made another typo.
So what equation?
Right there. The exponent, when you say the second exponential there, where you have a dagger b minus b a dagger.
Oh, the same mistake.
Same mistake you made last
Yeah,
time.
same mistake. Yeah, I didn't fix my. I did fix my notes. Yeah, the fix same mistake. Bidaga. Yeah, you correct me, but forget to
Twice.
correct me. Okay, and that's the most important term is this
And
one.
I think
That's
Muhammad has
why.
got the question too here
Oh yeah, I didn't
in the
notice.
chat. Uh,
Okay, let me read. How do you mean plus minus I exponential of I pi minus I? Yeah, because it's pi. Yeah, yeah, you are right. Yeah, I. Yeah, yeah, Mohammed is right. But anyway, it's just a contribution is just a phase, right? In the end, if you are looking for probabilities, so this I will not have importance. So it's here, right? Yeah, because it's sine, right? Yeah. Thanks. And then, yeah, the same thing here. So the conclusion here will be like the same, but just remember that C acts on the mode C, right? So these operators, uh, these creation and annihilation operators will act on mode C. And the conclusion will be like the same. They are phase shifters, and let me put you red, and they act like in a dual mode, A dagger A, C dagger C, apply, let's say, 1, 0, where we are using the convention is CA, okay? This is C, this is A. And if you do like the same thing that we did here, remember always that C applied to the mode C only, and A applied only to the mode A. So this will give 1, 0, okay? And the same for the others. I mean, you have always just a phase. Let me just put here all the expressions 0, 0. Again, this is the first is C mode C, the second is mode A. So these will give just 0, 0. And yeah, exponential I side 2, B dagger A, C dagger C, applied to 1, 1, CA. This will give only this one, CA, And let me write here, save space. Okay, the other is I side 2 A dagger A C dagger C 0 1. This is 1 0 0 1. So C A is always this order. C A C A, and here we have this 0 1. Doesn't change. And the same when we have the mode B instead A. The same for mode B. That's this term here. Exponential IC over 2, B dagger B, C dagger C. When applied to all these things, will be like the same thing, okay? 1 1 0, and now it's B A. Oh, sorry, C B. The convention, our convention is C B. So this is 1 0, and the same thing, okay? For the others. Not repeat. So, okay, so all these effects, it's contribute only with a phase. So they are not at all like fundamental. So all these effects are not fundamental and can be compensated. Compensate. The most important term the most important term is the second in that expression. It's the second in equation 748, which defines the quantum predicting operator. So the second term is this one. F of psi exponential psi over 2 C dagger C A dagger B minus B dagger A. Now it's writing 7.49. And it says like the usual like classical predicting gate is recovered when psi is equal to pi. And important to see that in which case when no photons are input at C mode, at C, then nothing happened. Like A prime is equal to A, and B prime is equal to B. We can check this. Let's say, let's consider this example. So F applied to the mode 0, 1, 0, where again, this is the mode C in our convention. You guys take care because sometimes you find different conventions, okay? When you're reading another books or papers. I'll show one example in, in, a, in a moment. So our convention is that C, B, A. C, B, A. So when we apply this to this state, we'll have, I'll write this in terms of a theta, just make the thing simple. Don't need to carry these two. And because it's easier to write a theta than a psi. So A dagger B minus B dagger A. So this theta here, or this applied to 0, 1, 0. And this what I call theta is just the psi over 2. Okay? And to make the conclusion is the same. I have a exponential operator, expand, this is like the identity operator, times pi. And because C commutes with A and B, so I could write this in this way. Minus B dagger A, B dagger C. Apply to this. And this is CBA, CBA. So these guys here, oh, plus high order terms, right? Plus, because it's exponential, high order terms. Apply to this. BA. So this will give like 0, 1, 0. And this guy here, when we applied C to this C mode here, it's an annihilation, so it annihilates the vacuum, the result is 0. So this is plus 0. And the higher order terms will contribute with the same because we will have like this term square. So this term square is C dagger C, C dagger C. So it's the same thing. Okay, so this is the nothing happening if again in the figure, let's show here. If no photon is coming in this wire here, in the mode C, so it's like this term works like identity, or it's like it's not activated, the nonlinearities, and nothing happened with the A and B modes. Will always be the same. Okay, but let's see, and you can like prove these two other combinations, but always let's see is 0, the other possibilities. But more interesting is when we have a photon coming here, and we'll see what's happening. Okay, so this is in general. So in general, we could like write when I have no photons passing from the K medium. Let's write 0 BA. Doesn't matter who B or A, who is a 0, 1 here. It will always 0 BA. Okay. Okay, and now consider a single photon consider consider that a single photon is input at C. Then A prime becomes B and B prime becomes A. Let's see this. So let's see an example. The Fredkin gate to 110. So again, this CBA. I'll write the gate here. Theta C prime C, A dagger B minus B dagger A, 110. So the same procedure. I'll make an expansion, but now I'll make the expansion to high order terms because we want like to get a general expression. So C dagger C plus the second term is this one. So A dagger B minus B dagger A. I'll write this way, okay? Square C dagger C square plus third term dagger B minus B dagger A to the cube, C dagger C to the cube, plus, you guys will understand why I'm going so far in a moment, because we see that this expression can be given in terms of sine and cosine, the general expression. C dagger C to the fourth plus the other terms applied to 1, 1, 0. So let's see all terms. The first term, this is the identity, will be the same. So let's see this term applied to these were effects. Dagger B minus B dagger A, C dagger C applied to this. So 1, 1, 0, where CBA. So C, the annihilate operator in the mode C, applied to the one photon state, they annihilate. So you have the vacuum now, but now this creation operator will create again the single photon. So, questions?
Yeah, Konstantin has a question.
Yeah, please. Okay, let me.
Why do you reverse CC
Oh, because
AB minus BA?
yeah, just to make the thing simple here, at least remember that it's not required. You don't need to do that, but just to show that the C, when applied here, the result will be 0, and because C A and C B commute, so I can do this, okay? Because they act in different modes. So I could have put this here and make the calculation for A, B, but when I make the calculation for C, the result will be 0. So that's why I put we will have like something multiplied by 0. And that's why I make first the calculation for C, because it's 0. So it doesn't matter the calculation for A and B. But here we could see like B, this A acting here will also give 0. But this term would be like different of 0 because A applied to 0 will give 1, and B applied to this one here will give 0. So it will be different of 0. But we multiply by C, that is 0. So will not change. So that's why I make only the calculation in C to see that the result is null, the contribution is null. And physically, it's because you have no photon going in the nonlinear medium. And the cross-phase modulation is exactly the interaction of two photons, one coming from one wire and the other coming from the nonlinear wire. So they have this interaction, and then you have the result. We return this when I finish here. So, but when we have no photon going from the wire C, the mode C, so the K medium is not activating. So nothing happened. Okay. So I'm doing here the same thing again. But here we can see that this is not 0 when I apply C to the modes C and apply to this guy. Because C applied to the mode 1 will destroy this photon. But C plus applied to the vacuum will create again. So we have this. This is the result of C plus C when we have C. So this is just 1. Because we annihilate and create. Okay? So this is the result. And now we apply these guys here in this state. So this is state CBA. So look, this A is applied here. This B we applied here. But again, A, this is the annihilate operator applied to the vacuum, is the result is 0. So this negative term is null. But now we have this positive term. So the positive term, we will have, again, this guy applied to here, and this other guy applied to here. Now, A plus applied to the vacuum, it will create this theta 1, that's this. This B applied to the single mode, this B here applied to the single mode, destroy the photon, and this is 0. And this applied to this, create this one. And we have this. This is state now. So this is the effect of this term. This term here. Okay. Okay, so let's do the same thing here. The second. So this is basically is A dagger B minus B dagger A multiplied by A dagger B minus B dagger A. It's this term that I call square. And C dagger C, C dagger C. Applied to this state. 1, 1, 0. So this is theta square over 2 factorial. And we know, again, these guys apply to this term here, that's the C, CBA. So destroy, create, destroy, create. So the first term is just 1. So this is dagger B minus B dagger A, and dagger B minus B dagger A, 1, 1, 0. And we know how this, when applied once, for this state is the first result here. So we just use this, and we'll find That is theta square dagger B minus d dagger A. And this applied to this is the result here in the top. Is just 1, 0, 1. And now we apply this. So A applied to this guy and B dagger applied to this guy. Now the negative will not be 0 anymore, right? Because the destruction go to 1, so now it's vacuum. B dagger, that's the creation, go to the vacuum, create one state. And the positive now, it's 0, because B, the destruction operator applied to this one, destroy, and we have 0. So the final result will be theta over 2 factorial, negative sign, that's the sign here. So 1, B applied to the vacuum, create 1, and A and B dagger applied to the vacuum, create, and A applied to the single faulty state, destroy, 0. And we can keep going doing that. Okay, not do the same calculation. So the third term is this term here, theta 3 factorial. So A dagger B minus B dagger A, and dagger B minus B dagger A square, because this is square we already know, that's stop here, the second. And we know that this C dagger C, when acted to the 1, doesn't matter this number here. It will always like destroy and create, destroy and create. So it's 1, 1, 0. So when you do that, the same idea here of just what the result is will give this one. And the other term, the expression theta 4 for factorial. This will give us like theta to the 4 over 4 factorial, 1, 1, 0. So when we like take all these terms and put in the expression for f, now expansion 1, 1, 0, we see that this is 1, 1, 0 plus theta 1, 0, 1 minus theta square 2 factorial 1, 1, 0 minus theta to the q 3 factorial 1, 0, 1 plus theta to the 4th 4 factorial 1, 1, 0 plus higher order terms, sum of the expansion. And this will give like 1, 1, 0 times 1, and these are the minus 2 factorial plus 4 factorial plus the others, and plus 1, 0, 1, and this term here, theta, minus this term here, theta factorial plus the others. And this is just an expansion for the cosine, and this for the sine. So f 1, 1, 0 is this cosine of theta 1, 1, 0 plus sine theta 1, 0, 1. And theta here, remember, is psi over 2. So f 1, 1, 0 is cosine psi over 2, 1, 1, 0 plus sine cosine psi over 2. Psi over 2, 1, 0, 1. And when psi equal to pi, so we have f of pi applied to 1, 1, 0. This this gives us this term, right? This is just 1, 0, 1. Okay. This is important. So what it's doing, I'm not return there. Remember the figure? It's like the Kerr medium. And we have like the beam splitters. So it's ABC. So when I have one photon in the mode C, this mode here, coming here, what it do, it's change the photon that was here. This initially the input is one photon here, in the vacuum here. And in the end, I'll have one photon here, and the photon that was in B comes to A in the vacuum. Okay? Nothing. So what the Fredkin gauge is doing is like that. And when this first term here is 0, it's act like identity. It do not. And we guys also can check. You check that F101 when I have the photon in A and not in B. This is cosine psi2 101 minus sine psi2 110. And when psi is pi over 2, F101 is equal to minus 110. Okay, it's again the mode ABC, ABC, ABC. Oh, sorry. Sometimes I get confused because I read different sources. CBA, 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 CBA. Okay. So once one photon here, and when I have the input is no photon in B and one photon in A, it's like just like switch. I don't know, switch the photons. That the photon that was here in B appears in A and vice versa. Okay. Question?
Yeah. The negative sign in front of the result.
Yeah, it's just a phase in the end. Yeah, in the end, it's just a phase because you want to know like the probabilities. So this minus sign goes out.
Right.
It's not that important. The physically, what's important here is just that we are switching, right? So I think the switching the photons in that was here in these wires. But this happens only when you activate the nonlinear media. That's why you have like the the cross-phase modulation, right? That's the
Hmm.
this relation. The photon that comes here um, uh, interact with the atoms in the medium, and the atoms in the medium interact with the photon that come in the other way. That's
I
it.
have a second question, Carlos. Now, you did this for when the angle is pi.
Yeah,
Uh, if the angle is not pi, is what you're getting back a superposition?
yeah, superposition. Yeah,
Is
yeah.
so
You
this
will have like some probability to find the fault here, and some other probability to find the fault up here. In this way, when it's pi, the pi, right? I put here pi over 2, what's pi? When psi is pi, so you have 100% of chance to find the photon in one or the other.
so another application of this gate could be to create a superposition.
Yeah, yeah. If for different angles.
Okay.
Remember that the angle is related, this psi here originally, physically, it's related with the susceptibility that is here, like that tensor of susceptibility times the distance, the length.
Thank you.
So okay, we are done with this part, and I would like to have an application that I'll try like in 50 minutes just to give some idea at least about one very nice exercise that is in the New Century book. Yes, this one. Exercise 7.13. You guys can see and read well. That's the book, New Century book. So exercise 7.13, like he says, in section 144, page 34, we describe a quantum circuit for solving the 1-bit Deutsch-Jozsa problem. Here's a version of that circuit for single photon states in the dual rail representation using blink splitters, phase shifters, and nonlinear Kerr media. That's what the tools that we are dealing with, we are studying. So this is a very nice exercise, like to solve an algorithm, a real algorithm. So what's the physically is happening in the quantum computing? But unfortunately, we don't have so much time. And I mean, the continuation of the problems here. That's the book. So this is the same problem. So the problem starts here, and so it have the box that we just explained, and this is the continuation of the problem. He show like a circuit like that, and he basically wants you to find the oracle, right? It's U of F. And he has construct circuits for the four possible classical function U of F using Fredkin gates and B splitters. Why are no phase shifters necessary in this construction? For each U of F, show explicitly how interference can be used to explain how the quantum algorithm works. And does this implementation work in the single photon states are replaced by coherent states? So we don't have so many time, but let me at least give some idea. As far as I know, we don't have like official solutionary for this book. So if it exists, I don't know where it is. So you guys can find a lot of exercise in the internet that people make in internet input, but I didn't find a good for this in particular. So I was like making some research, and then I found this paper. This paper here that, if possible, I will give available for you guys. It's Simple Quantum Computing by Shuang. Shuang is the same from the book, but with a different collaborator here. This Yamamoto is a Physical Review A. from 95, so before the book was written the first time. And the problem is actually the Deutsch problem. So we will not have time to discuss the Deutsch algorithm. So here is the idea from the algorithm here. They put in this diagram, the algorithm for solving Deutsch problem using quantum computing. And the optical part here will use basically the things that we use. That's the quantum beam splitters, the quantum Fredkin gate that we are using, phase modulator, that's the phase shifters we are calling, phase shifters, we call here phase modulator. And the only different thing that we didn't discuss is the classical switch. That basically what it do is when this k here is 0, so a prime, a prime is equal to a, b prime is equal to p. So basically when k is 0, it's like the switch is off. And when k is equal to 1, it switch a and b here. So it's on. It's basically this. And here he proposed the circuit, like the physical circuit. Here's the discussion about the algorithm, and the circuit, the quantum circuit is this, something similar to this one. So I think it would be very interesting that you guys try to read and solve this, apart from the fact that he is considered, but you guys can consider here in the order he is considered A, B, C, D. And we are, in the book, we are using the opposite, D, C, B, A. A is in the, close to the angle. But physically, this will not change. I mean, you guys can use here, his notation in the paper. But the only thing that is I found here one mistake, and when he applied this S operator here. So let's see. Let's try to, like in 50 minutes, something like that, do something about this exercise, just to give the idea. So, but this is not the only circuit possible. You could have different ones. This is just the one that I found, and I think would be like simple. But you can, like, you're free to try to solve the problem. Use different versions. So exercise 7 of 13. And okay, the way I will try to preserve our notation here. Okay, we'll make some changes from the things he did, and just for the ones that not familiar with the Deutsch JAWS algorithm, will not have time to discuss, but you also can read in the paper, but you also can read in the Nielsen-Schoen book. It's here in section 144. That's well explained here. Okay, all the math and the circuit, like this is a general idea, the circuit that would like solve the algorithm. That's for n qubits. The case we will consider is only 2 qubits, the exercise. And here's the algorithm you guys can read. And basically, let's see the summary here. You input some numbers, like here, he's input 0 in the top and 1 in the end. And do the things that you need to do here in this oracle, in this U of F function. And in the end, the output, if the output is 0, so F is a constant function. If the output is 1, F is a balanced function. Okay. So to understand the better the algorithm, I suggest you guys to read here for the ones that are not familiar. So let's see at least some basic things. Exercise 7.13, and I'll try to do, let's see, because I don't want to draw. I don't want to draw that circuit that's too big, and to save time, let's fix this one. Okay, it's the circuit, just okay, I think it's much better. That's basically the circuit that we consider. The only change, I will do some changes here because to adapt to our notation. So I will consider this dy here, this not be zero like in the paper. Oh, I cannot, I thought I could. Fortunately, the program don't let me to write here. Right here. Yeah. So this will be 0. This is 0. This will have 1. This is 1. This 1. And this is 0. Okay. It's just the two in the top. This is 0, this is 1, this is 1, this is 0, because I want like to follow. Remember, the notation that I'm using is different from the paper. When you guys will read the paper, so I'm using this notation, this CBA. In this case, I will consider D is equal to 0, C is equal to 1, B equal to 1, and A equal to 0. Okay? That is our notation. So if we remember so this is we are not in the logical zeros in one. This is just like the vacuum or if it has a photon. So initially we have a vacuum in D, one photon is coming here, one photon here in vacuum. So this, in the logical, we are consider 0, 1 is the logical 0, and 1, 0 is the logical 1. This is okay. That's to be agreeing with what the book, when explaining the algorithm, is considered in the top 0 and in the bottom 1. But this is the logical. So it's not vacuum, not photon, it's just the logical 0, 1. It's not decided what it is. In our case, in optics, in the dual ray representation, so in the top, this is the 0, and in the bottom, this is 1. Okay? And so we have 4 possibilities that is related with this K. So let's just look here. The first possibility is when K1 equal to K0 is equal to 0. K is here, K1 and K0. It's exactly the guys that turn on or off these switches. Okay? So when K is 0, Remember from the paper, K0, K0 or K1? Go to 0. Right this way, like in the paper. So this, the classical switch. We have one wire here, the other right here. Let's say A, B, A prime, B prime, and here K. When K is 0, this is when K is 0, so it's off. And the other situation is this. A, B, so B prime, A prime. Okay? This is when K is equal to 1. Doesn't matter if it's K1 or K0, it's the same. And K1 is acting the top. So this is our like Fredkin gate that we just studied. This is just a phase shifter here. That's problematic and we see why. And this is again the same. So this is U of F, and this is like U of F again. This is a B splitter. B splitter. This is the B splitter diagram. In the end, you measure. Okay, so the first case, K1, K0. So these guys are off. Okay. When these guys are off, so the initial state is psi 0. Psi 0 is here, the beginning. So this is psi 0. Is the initial state 0, 1, 1, 0. I'll always put this to don't get confused because I get confused. So this sequence, so this is the first. The second is psi 1. Psi 1 here, the only thing we do, the problem is I need to be moving always. So psi 1 will apply the beam splitter in the DC gates, okay, DC wires in psi 0. In the BA wires, we do nothing. This is just. So, okay. So psi 1, B applied in DC, psi 0. So remember that the B splitter act like a 50-50 B splitters, okay? This is a 50-50 B splitter. It acts like a Hadamard gate. So this will give us this thing here. And this is the logical 0. So the Hadamard gate, when applied to the logical 0, gives a superposition of 0 and 1. 0 plus 1. When Hadamard is applied to the, just to remember here, Hadamard, the logical 0, gives 0 plus 1. And Hadamard applied to 1 logical gives 0 minus 1. Okay? But this is my CDC, so it's applying in the DC wire. This is the 0 logical. So in terms of this notation, we have the 0 logical, that's 0, 1, plus, and not minus, 1, the 1 logical. The 1 logical is 1, 0. Okay? So this is DC. And times the other terms that's we did nothing in the beginning. 1, 0, B, A. Okay? Okay, so the next we apply psi 2. Psi 2 is exactly we apply the oracle. In this case, when k1, k0 is 0. So when the function f is 0, 0, apply psi 1. But because the both switch are off, so nothing will happen here, right? Because this is off. Look, we come here. Uh, the photon initially was here in C. So the beam splitter put this photon in superposition. So it has 50% to be here or 50% to be here. Let's say that he comes here. If you come here, you find this switch. If the switch is off, K1 equal to 0, so it just pass here. It will not activate the kernel. That's the case that we are considering. But when K1 is 1, so the switch is on. So what the switch do is put the photon that come here in C and put in this state, and come here and activate the kernel. But it's not the case now. Okay, the switches are off. The first example. So okay. So psi 2. So this works like identity. So since K1 equal to K0 equal to 0, switch 0 and switch 1 are off. So UF 0, 0 act like identity. So nothing will happen here. Psi 2 is the same as psi 1. And then he asks you to put a phase shifter P in the wire A applied to psi 2. Okay, let's see the figure. See the figure here. So all these things is like the identity in the first case when the switches are off. And now I have psi 2. We are here in the circle. And now we apply this phase shifter or phase pi. And then we have the psi 3. Then we apply again the oracle. But the switches again are off, so it's like identity. Then we will have psi 4, and then we apply the beam splitter, and we have the psi 5. Okay. So okay, but now we are here. Oops. So psi A, pi 3 is psi A. Just to remember, P when applied to the vacuum is just the vacuum. P when applied to one state is -1 when the angle is pi. And then we have psi 3 is equal to PA psi 2. Psi 2 is psi 1. Who is psi 1? Psi 1 is this guy. And A is 0. Okay? A is this guy here. So P applied to 0 is 0. So psi 3 is the same as psi 2. And psi 4, we apply the UF dagger to psi 3. But UF dagger is the identity dagger. The identity dagger is just the identity. So this is psi 3. And in the end, psi 5. that is B dagger in the Y DC in the top applied to psi4. And psi4 is equal to psi3, that's equal to psi2, that equal to this guy. Okay, this is psi1. So equal to this. So just write here. So psi5, this is like psi1, so it's B dagger DC is equal to psi1. Applied to psi1. And this is B dagger DC. That's right here. Psi1. 0, 1 plus 1, 0. DC times the other values. 1, 0, BA. Okay, when we apply this here, it's like a Hadamard. When we apply Hadamard for the second time, this will become the original, right? And remember, when we have like a sum, this will give like the zero logic. That's in this case, it's just the 0, 1 state. So we have this DC times this 1, 0 BA. That's the same as 0, 1, 1, 0. That's what we'll read. And this is the, in the top, that's in DC. This is DC, this is the logical 0. This is the, in the bottom is the logical 1. So in the top, if you see the algorithm suggested, when we read 0, it means that the function f 0, 0 is constant. What's the case, right? Because it did nothing in the oracle. Nothing happened. Okay, so this is the simplest case, not funny, because it basically we did nothing. It's just to you guys like see the what we were doing. So the second case is when k1 is equal to 0 and k0 equal to 1. So in this case, just the bottom switch is on. So this switch is on. So we have all these things. We pass from, this will not be activated again because the switch is off, the K1. And the only thing, the B and C here, the photon will exchange, will be switching because this is on. So I'll not repeat all these steps because of the time. I'll just put here the answer and you guys can confirm, okay? If we do like the same procedure, so again, psi 0, it's just the initial state. This will never change. DCBA. Psi 1 is when we apply the beam splitter. And psi 0, which will give this 0, 1 plus 1, 0 DC times 1, 0 BA. And then beside 2 is UF01 psi 1 and switch 1 is off and switch 0 is on. So because switch 0 is on, what it do is exchange A and B. Okay. So the final answer, you guys can check, will be something like this. 0, 1 plus 1, 0 DC times. So because switched here, so we'll switch these guys. 0, 1, B8. And side 3 will just a phase in A, side 2. Now the phase is applying A, applied to the one photon, and just change the sign. So this is minus 1 square root 0, 1 plus 1, 0 DC times 0, 1 B8. And then again, side 4 is UF 0, 1 dagger applied to side 3. Side applied to side 3. And the same thing, the switch 1 is off, switch 0 is on. So again, we just change A for B. A for B. So the only thing the switch do, is you do, side 4, is switch again these guys. So the minus 1 square root of 2, 0, 1 plus 1, 0 DC 1, 0 BA. And psi 5 it doesn't tangle on this guy. So if B dagger psi 4, B dagger is acting in DC. So it's acting this. And this sign is plus. So this is minus the logical 0, 1 times this, that 1, 0. So again, this is the logical 0, this is the logical 1. But we measure in the top, so we measure this one. And the function f 0, 1 is constant. Right? Because when it's 0, when you guys look for the algorithm in the book, you see that when it's 0 in the top, 0 logic, so the function is constant. Okay, so in the interesting case, let's see the time. Yeah, I think we could discuss. You guys should try to do this. K1 equal to 0, K0 is equal to 0. So the same steps, psi 0, it's the same thing, 0, 1, 1, 0, psi 1. Again, we just apply the BDC to psi 0, give the same, 0, 1 plus 1, 0, DC, 1, 0, BA. And now, in the psi 2, UF 1, 0 to psi 1, switch 1 is on, and switch 0 is off. So when switch on is on, we will activate the Kerr medium and the Fredkin gate. It's not saying anything, but I'm consider that the zeta equal to pi. Okay, so it's like a classical Fredkin gate to make the thing simple, but it can. We have the answer that we want. So when you do that, you'll find, and just to remember, like the Fredkin gate used this 110. We just prove CBA. This is 101 CBA, and the Fredkin 101 CBA is just minus 10 CBA. Okay, and Fredkin when C is 0, doesn't matter who is B and A, the result is like the identity. It doesn't change. So, okay, if you guys do this, you guys will find side 2 is this guy here. 0, 1, 0, 1, DCBA plus 1 square root of 2, 1, 0, 1, 0, DCBA. And then the problem here is in the step 3. You guys, you see, when you put this here, should not have this phase shift here. I'll try to explain why. So this, when you apply this here, it changes the sign only when A is 1. So only this first one, here A is 0. So this is minus 0, 1, 0, 1 plus square root of 2, 1, 0, 1, 0. And then we return it, and I'll explain why this guy should not be here. And I think answer one of his questions. F10 dagger applied to side 3. So using the same thing, we will find that psi 4. So this is the Fredkin. So psi 4 is 1 square root of 2, 0, 1, 1, 0 plus square root of 2, 1, 0, 1, 0, which is the same writing this 0, 1 plus 1, 0 times 1, 0. This is BA, this is BC. And the last step, psi 5, we applied B dagger DC to psi 4. And this will have plus again. So this will give like the logical 0, 1, 1, 0. But should not be, this is the logical 0. This is the logical 1. But again, in the top is 0. So the function is constant, but should not be constant this time. And the problem is exactly because we applied this guy here in the step 3. When we applied this guy here in the step 3, it changed the sign. It changed the sign here. So if we don't do that, this will be positive. And when we apply Fredkin here, because here I didn't show the details, let's see. When we apply Fredkin here, what we'll have, remember that Fredkin doesn't act on D mode. So we'll have like this first is 0, this is D, times Fredkin that acts CBA in 1, 0, 1. This should be plus, right? And plus 1 square root of 2. This mode is, the first is D, times Fredkin 0, 1, 0. CBA, CBA. Well, Fredkin when C is 0, it's like the identity. So this doesn't change, 0, 1, 0. And Fredkin acting in this guy here. Let's see where I put it. predicate acting in 101 is just minus 110. So when we apply this, this become minus, and when applied predicate, this, okay, let's see, initially what we did. So because we applied this phase shifter here, P, we applied here, so this was plus and plus. We applied here because P applied to one photon state, P is PA, so it's the YA, so we change this sign here. DCBA, DCBA. So the sign changed because the A. Here it did nothing. So we have this. But when we applied predicate here in this first case, it changed the sign again. And here predicate do nothing. So it becomes positive and positive. And in the end, you have like the, because this is positive and positive, so this is the logical zero. But if we don't do this step here, this third step, don't do this. So this psi 3 should be just the psi 2. So this is positive. We don't have this minus. And this minus here will leave the first term negative. So when we apply this predicate here, this guy that's positive becomes negative. And yeah, this get term is negative, and this will be like this is the logical zero, this is the logical one. So this, when we apply the Hadamard gate again, this will be minus the logical one. So this will be 1, 0. So this is the logical one. Yeah. And when we find F, when we measure the top one, so F10 go to 1, it means the function is balanced. And you can do the same thing for the other case when the fourth case, when K1 equal to 1, K0 equal to 0. In the end, but only really the final answer, not consider the phase, you can do the same, the two ways, with the phase and without the phase, and we'll see the same problem. So we find here, without the phase, without the phase shifter, we find this is minus 1, 0, 1, 0, DCBA. And again, this is the logical one. Okay. So, okay. And the function f is balanced, f11. Okay, guys. I need to finish here. So I will stop the recording because otherwise the video would be too big. But then we still have like 5 minutes to discuss.